introduction. So yes, I'm Avinanda Chakraborty. And first of all, I would like to thank to the organizers for giving me this opportunity to present and participate in this extremely important and relevant conference. So this work I have done as a postdoctoral researcher at INAF Archetri in Florence. Yes, so this is the outline of my work. I would like to explain about the method and the instrument and also the data reduction and analysis and the results and conclusion at the end. So I have used the data of ERIS, which is the Enhanced Resolution Imager and Spectrograph, which is an instrument at a very large telescope. Just like Rajeshwari earlier mentioned about the MUSE, it's another instrument that is installed at VLT telescope. So VLT has 4 telescopes. It is installed in the 4th telescope of VLT. And so ERIS is a new generation AO assisted instrument, and it combines adaptive optics, imaging and spectroscopy, and it is designed mainly for the high resolution studies of galaxies, stars and exoplanet. Okay. So, and it uses integral field spectroscopy. And for those who are not familiar with this IFS, so IFS combines spectroscopy and the imaging. So basically each pixel not only have the information of the imaging, but also has the wavelength distortion, so which means like the full spectrum. So that's why the output is called data cube, because it has 3 axes, basically the image axis and the wavelength axis. And this is the spectrograph of ERIS, which is the SPIFR that I use. Okay, so I'm part of this ERIS GTO program, which is the PI is Dr. Francesco Belfiore. So this program is about to study 20 star-forming galaxies at cosmic noon to study their baryon cycle. But in this work, I would like to talk only about this particular galaxy because this has the best resolution so far for all our observations. And so this is a galaxy at redshift 2.19, and we can see this is a clumpy ring-like galaxy, and it has a stellar mass of 4 into 10 to the power 10 solar mass, and this radius is 4.6 kiloparsec. So are we the only one studying this galaxy? No, there are so many work on this but galaxy particularly, so we can see the works, and there's a very recent one as well. So is everything already observed so far? No, of course not. So I would like to draw an attention to this. So this is a spectral analysis which also I have done, but I would like to draw your attention in this particular H beta emission map, where we can see the H beta is only detected in this clump, or only one clump. And this H beta is very important. So why is H beta is important? Because the ratio of H alpha line and H beta line like tells us about the dust distribution, dust extinction. To get the actual flux, we need the H beta. It's very important. And so far all the works couldn't have that H beta information. And so these are the other importance. So far all the works on this galaxy was done by Symphony. So ERIS is basically the successor of Symphony. So it has like all these better qualities than Symphony. And also, not only it's a better instrument than Symphony we are using, it also like we are using the newest data. So some of our data are collected in this year. So also it's a clump-like galaxy, as I already stated, but these clumps for all the other works are only like previously they are defined as for the eye estimation. There is no there's no actual identification how to define the clumps, but for our case we are defining the clumps using a Python code which is considering the maximum value and then defining the clump. So it's a more like a robust analysis we are using, and hopefully we are trying to get the H beta so that we can actually get the dust estimation and dust corrected flux. So these are the data I have used. So H band data, these 3 bands data, and for the simplest way, so I can say from here the take on is from this slide. So H band, so this galaxy has been observed for 32 times in the H band with a total indication time of this, and this J band for 22 times for this total indication of this. So J band and H band data are the part of our GTO program, and these data we got from our collaborator in MPE. So now, because we have observed this galaxy in different dates, in different bands, to now combine all the data to get the actual combined cube, we took the help of this PSF stars. So to calculate the offset, because this is a galaxy is a faint object. Also, though it's a AO adaptive optics corrected data, but to actually get rid of the absorptions, the atmospheric absorption and emission, we also took the help of the telluric stars as well. So, and also, like, because the besides those, the PSF looks different for different bands, so that's why we also corrected for the PSF. We smoothen the data to actually compare different emission lines. Okay, so now it's time for the results. Okay, so this is how we define, these are the clumps, how the clumps look like. This is how we define the clumps, and this is the brightest clump, clump 1, and here we can see the spectra of different emission lines. And for the H alpha and O3 emission line, we can see it has another component of Gaussian, and it has the component is slightly asymmetric as well, so which is an hint of stellar outflow in the clump. And also for these clumps, we can see that was like lagging. I mean, in clump 1 it was already detected, but we also detected H beta as well, and this is the only clump where we detected N2 as well. Okay, so for the next brightest clump, we detected H alpha and O3, and it also has a like a second component, an asymmetric one, so it is also a hint of stellar outflow in the clump. And for the third clump as well, third brightest clump as well, we got this outflow hint from this two emission bright emission lines. And next, for the next clumps, because we are not getting any outflow signal, so we stacked all the other clumps from 4 to 12 except for this 06, like 6th clump. I will come to this later. So we didn't found any outflow signature in these brightest clumps. Okay, so now what is interesting in this clump 6, which is here, that for that clump, we are getting very high broad component of the H alpha emission line. So the full width half maximum is greater than 1000 kilometer per second. So, and which is not expected from a star forming galaxy, because this is kind of, this is what we find in an AGN. So there is a possible, like, we cannot say anything, but there is a possible hint that there could be an off-center AGN at this clump, at the position of this clump, and also like the simulation of the ring galaxies that supports, in some of the galaxies we have seen this off-centered AGN. So this is like a hint, but to know more about it, we need to analyze it more. So this is a very recent analysis. So we missed the JWST deadline this year, but we are preparing for a JWST proposal next year to get the faint emission lines like helium, so that we can say if there is an off-center AGN present in this particular clump at this position. Okay, so the main highlight, as I said, like, because we are lacking of the H beta detection, but in several clumps we detected H beta emission from our observations. Okay, so we didn't stop there. We then try to get the map, emission line map, and for that we used IFU feed code, which is basically a Python-based code which feeds the simultaneously all the lines, and also it takes like the Gaussian kernel we have used for 1 pixel for this code. And I'm showing for the H beta and H band and the K band. Okay, so these are the emission line maps we have got from this IFU code, and here we can see that the H beta is like detected in most of the part of this galaxy, and that's a very good sign. And to get the dust emission, we also need the H alpha that was already found by the previous work, but we also found this, so that's a very good sign that we can actually get the dust emission. And from that we can get rid of the dust extinction and get the exact more accurate values of the flux. So that we get the AV map, and we actually got the extinction corrected emission line maps from for all the lines. And not only that, we also got the line ratio maps. And so this line ratio maps actually tells about which emission line dominates in which part of the galaxy. Okay, so all this analysis helps us to actually estimate these outflow properties and the SFR. So we could estimate the SFR, H alpha and O3 outflow velocity, outflow rate, mass outflow rate, and also the ionized mass. So these are the clumps and properties we have estimated using the like all the analysis. Okay, so here I already spoke about the H band and K band, and here we have done the similar spectrum analysis for the J band as well, but this data is very noisy, and probably it requires more deeper data as well. So we can see that we found that the H band in J band, O2 is detected in only 4 clumps, that is 1, 2, 3, and 9 here. So these are the O2 detected O2 emission lines for all these clumps, what we could achieve from whatever is available currently for us now. So using this O2 and previously estimated O3, we could actually got these physical properties, the electron density, metallicity, and ionization parameter. So metallicity is subsolar, which is actually like supporting the previous literature as well. Okay, so what's next? Because I have done some spectral analysis and then got some numbers, but how to know how it's correct, like how to validate that? For that, what we are currently doing, we are combining our ERIS data with the JWST and the HST archival data for that galaxy, and trying to get the ACD feeding and trying to extract the metallicity and the SFR, these two properties specifically, so to match with our results so that we can validate our results as well, that what we are doing is correct. Okay, so this is the summary. So we got that the data is better quality. We also found that H beta detection in most of the clumps. Here I forgot to mention that in all the clumps we have found that H alpha is greater than O3, which basically states the star formation is dominated by the extinction. And so we got the dust extinction corrected kinematics because we could estimate the dust extinction. And there could be, and that's the most interesting thing, is there could be evidence of off-center AGN, and we are now trying to validate our results from the ACD feeding. Thank you.
Thanks, Avinanda, for the very nice talk. Yes.
Thanks. So I was wondering, I'm quite curious about your plausibility of an offset AGN. So I was wondering about what evidences are you going to look at, or what are the other plausibilities, if not Asian, in terms of that broadening you have observed in the?
So there could be supernova explosion, for example, but so what I can tell you so far is sorry. So this is a simulation of the ring-like galaxies with an intruder present. So there's work going on with one of our collaborators, Michele Parna. So he is working on this ring-like galaxy with an intruder, and you can also find that in JWST we have seen an intruder here as well, like yeah. So this is following the same kind of ring-like galaxy which he is currently working on, and he found that in some cases in the simulation that there's a possibility that the AGN can be off center. So we got these two like hints. Now we are going for the faint line detection. So if we can detect, for example, helium, so we are planning for JWST near cam observation next year. So if we can find, then we can talk more about it.
Thanks.
Avinanda, good talk. It's me.
Oh,
Yeah.
sorry.
Okay, so my question is also on clump 6. What was not clear to me. So what are the sizes of your clumps? Like in parsecs, how big are those?
So it's not fixed, like as you can see.
No, for clump 6, I'm interested in clump 6. What is the size? Give me a sense. Like, is it kiloparsec or parsec, or what is it?
No, it's sub kiloparsec, like around 50 parsec you can.
So it's a 50 parsec thing.
Yeah.
And the spectrum that you showed, is it an integrated spectrum, or is it spectrum of one voxel?
No, it's integrated spectrum, like all the pixels.
Yeah. So then I will have some concern about the spread that you are seeing. So basically, when have you tried to look at the slices, like, and just to see? So the neighboring pixels, do they also show the same spread? Like, what is the, because you have 3-dimensional information, but the way I see the analysis has been done is more 2-dimensional.
I know.
Kind of a thing.
I can agree to that. I mean, so honestly, no, I have to say that I have not seen that. But so initially when I was following, I can tell you, like initially I was following the clump classification as the like the previous literature have done, and I couldn't find anything there. So it's like, it's basically, so it can be an art, like some artifact or something.
Yeah, it can be a sort of a superposition effect.
Yeah.
So what is a good thing and a standard way that is used for resolved spectroscopy? This is, you do not have a resolved spectroscopy in that sense, like your instrumentation profile which decides, instrument profile which decides. You do a channel map. Like you take in the 3rd dimension. So basically you make intensity plots of each of the velocity channels.
Okay.
Then you will see if you have correlated structures.
Yeah, that is actually I'm currently doing, like the plotting the velocity map and working on that. Yeah, that is like I'm currently working.
Yeah. Okay, good.
But thank for the suggestion.
Okay, let's thank Avinanda once again.